Good morning, everyone. My name is Cassidy Vaccari, and I have worked this summer alongside Dr. Matthew Scarborough to attempt to reduce greenhouse gas emissions at Shelburne Farms through the analysis of biochar-related technologies on their current waste management. I'd first like to acknowledge the Barrett Foundation and the UVM College of Engineering, Mathematics, and Science for granting me the opportunity to conduct this work. I'd also like to thank Marshall Webb, the Carbon Drawdown Coordinator at Shelburne Farms, and Mark Easter and Haley Nagel for their guidance and support throughout this project. I will begin with demonstrating the need for this work and introducing Shelburne Farms and our target technology, biochar. From there, I will explain our methodology and project timeline, and the results for our work will follow. Some likely next steps will be presented in looking forward. The global human population continues to rise. According to Our World in Data, the world population is projected to reach nearly 10 billion by 2050. In order to provide the food for this growing population, agricultural productivity will be in the forefront of priorities. Currently in agriculture, greenhouse gases are emitted from machinery, over-farmed land, enteric fermentation, and through manure stabilization processes. Combined, these result in a total of nearly 668 million metric tons, about 10% of all greenhouse gases produced in the U.S. each year. High levels of off-gassing of methane, nitrous oxide, and of other harmful gases directly into the atmosphere from each of these contributors makes up the agricultural greenhouse gas sector. Shelburne Farms, our target location for our work, would like to lessen their contribution to that daunting number and reduce their carbon footprint. To quantify and work towards that goal, they appointed Marshall Webb, a carbon drawdown coordinator, and preliminary meetings with him helped us understand their need for this work and their mission of becoming carbon negative by Earth Day 2028. Shelburne Farms is a 1,400-acre working and teaching farm located along the coast of Lake Champlain in Shelburne, Vermont. The vast land is comprised of farm, dairy, and educational barns, a bakery, restaurant, and an inn, all of which contribute to their carbon footprint. Our mission is to aid them in reaching their goal by assessing various alternatives to their current animal waste practices in hopes to reduce the impact of their animal agriculture. Exploration of biochar as our target technology led to a number of proposed solutions. To introduce biochar, I will present some of the key characteristics and properties that have made it so beneficial to agricultural practices in the past. Some common uses of biochar were explored and the most applicable were assessed for its impacts at Shelburne Farms. Biochar is a carbon-rich charcoal made from pyrolysis, a high-temperature, low-oxygen combustion of various biowastes. Within the past 10 years, its prevalence in recent research has rapidly increased. Common uses of biochar include soil and compost remediation, climate change mitigation, and our main focus, animal waste management. Its impact can be attributed to these key properties. The porous structure and great sorption capabilities allow for increased carbon sequestration when applied to soils. The large surface area and basic pH regulates and stimulates the microbial activity and enhances soil processes. Recent analysis suggests that biochar has the potential to reduce greenhouse gases from manure enteric fermentation when used as a dietary supplement and manure stabilization when added to compost. Mechanisms for biochar are not well established, however, they're likely due to their sorption capabilities and its capability to sequester gases in the rumen before they are released. Biochar supplementation to compost is a more common application. Here, biochar works to alter the microbial activity by providing nutrients and surface area for growth. Growth on the biochar surface enhances stabilization of organic materials by enhancing access to the oxygen required for the microbes. Benefits of biochar supplemented composting include reduction in greenhouse gases, odor control, increased degradation of organic materials. And so this generated our three main focuses regarding biochar. How would the addition of biochar to the cattle feed impact the emissions from enteric fermentation, how would the addition of biochar impact greenhouse gases from the compost of cattle manure, and then further exploration of the production of biochar and whether on-site production could further reduce their carbon footprint. Shelburne Farms has a significant history of environmentally conscious field practices. Due to nearly 30 years of rotational grazing, their soil organic carbon level likely has reached its maximum, which deterred us away from also exploring biochar as a soil amendment. So to conduct the analysis, the Comet Farm greenhouse gas accounting system was used to both estimate the current levels at Shelburne Farms and to assess the proposed solutions. It was created at Colorado State University in conjunction with the United States Department of Agriculture. The system allows the user to generate baseline emissions values and hypothetical future scenarios to represent alternative management practices, which allows the user to track carbon changes. It allows the user to input data specific to their farm regarding animal, land, and forestry agriculture. However, for our purpose, we just explored the animal agriculture side of it. Here's a few examples of common input examples. It asks for animal details like cattle weight and population and the feeding situation. For our purpose, we focused on just 5 types of cattle that were present at Shelburne Farms. Here, the baseline report was generated using values from Marshall Webb, who provided values that represented their current, and the total resulted in approximately 780 tons of CO2 equivalents per year. The common model measures things in CO2 equivalents, which is just a measure used to compare the emissions of other greenhouse gases by converting them to the equivalent amount of CO2. So this project proceeded into 2 phases. After preliminary work in the spring, talking with Marshall Webb and conducting preliminary research, we settled on a plan for the summer. It went through in 2 phases. In phase 1, I conducted a thorough literature review of biochar and its various uses and solidified a baseline model of Shelburne Farms with the help of Marshall. And in phase 2, we determined emission reduction potentials from the lit review and analyzed its impact, the impact of biochar in each alternative management proposed for Shelburne Farms, and also explored some on-site versus off-site production. After the generation of the baseline model, we began analysis, and this was done in a series of 3 steps. Collecting reduction potentials from the literature review, creating a set of high, low, and average values for each waste management, and applying these values to the baseline emissions from Comet. It's important to note that the values attained from the literature review were not produced from congruent processes. There's a lot of variable factors when producing biochar, like temperature and feedstock type and residence time, that all affect the final product. So to account for this, we created the set of high, low, and average, resulting in a range of results rather than just a single value. In order to assess the impact of biochar added to the cattle feed, we had to first determine the current greenhouse gas emissions from enteric fermentation. And this was done just through Comet. The report shows a breakdown of the sources of the emissions, and the enteric fermentation represented roughly 420 tons of CO2 equivalents per year from each cattle source. The use of biochar as a feed additive is not predicted to impact the nitrous oxide emissions, so it wasn't included in the analysis of this alternative. From there, the set of previously determined reduction potentials from the literature review were compiled, and the highest, lowest, and average were determined, and we found that using biochar could reduce methane emissions by 10 to 22%. We then applied those values to the roughly 420 tons of methane in CO2 equivalents per year, and that resulted in a potential reduction of 42 to 92 tons of methane per year. Composting is not used at Shelburne Farms currently. The impact of composting alone was first done to determine the baseline for this situation. This was done by altering the manure management system types in each to each of the 4 composting.
2 minutes.
2 minutes, awesome. Composting that can be modeled in Comet Farm. This includes in-vessel, static pile, intensive windrow, and passive windrow options. However, the windrow options are not feasible at Shelburne Farms, so only the in-vessel and static pile options were really focused on. And the difference of the selective in-vessel was that only the dairy lactating cows were altered. That's because just through looking at the analysis, it seemed that that was the only type of cattle that really had an impact, so had a positive impact. And that they both resulted in nearly 180 tons of emissions and CO2 equivalents reduced from the total. Reduction potentials were determined in a similar way as the feed additive. For methane, they range from a reduction of 17 to 82% with the addition of biochar, and for nitrous oxide, it was a range of 26 to 80%. And when applied to those, when applied to the baseline emissions determined, the in-vessel and static pile compost represented an average of 310 total emissions reduced, and the selective in-vessel compost with the addition of biochar resulted in nearly 300 tons of methane and nitrous oxide reduced per year. This alternative resulted in a total with composting alone plus the addition of 691 tons of CO2 equivalents per year, which is nearly a 79% reduction, which is the greatest among all proposed solutions. We used this to determine the potential impacts of biochar production. We selected the selective in-vessel composting scenario because it provided the greatest reduction. And so it was chosen to estimate the biochar demands and biochar impacts. From values in Comet, I was able to generate that the yearly manure production from dairy lactating cows is nearly 428,000 pounds per year, and common biochar application rates to compost are generally 3 to 50%. However, anything greater than 10% is discouraged due to adverse effects on compost process. So we chose 10%, and therefore yearly biochar demand is nearly 42,800 pounds per year, or 19.4 metric tons. Emissions from productions were determined from a study of the life cycle of biochar, and found that a combination of the transportation of raw biomass, feedstock processing, and pyrolysis all in total generated approximately 0.1 pounds of CO2 equivalents for every 1 pound of biochar produced. So in total, the production of 19.4 tons of biochar would result in roughly 1.94 tons of CO2 equivalents per year. Additional impacts of transportation to assess the offsite outsourcing option was done using a source that Shelburne Farms has explored before from Quebec, which is a 358-mile trip. A standard freight truck emits roughly 162 grams of CO2 per ton mile of travel and can carry nearly 40,000 tons of weight per truck. Therefore, combining all this, the total CO2 emitted during transportation is roughly 1.24 tons, and therefore the production process and transportation combined results in 3.8 tons of CO2 equivalents per year if we were to outsource the biochar. Aside from biochar, we use Comet to assess a quick fix for Shelburne Farms. A quick alternative would just be the installation of a cover over the current open air manure lagoon, which is their current waste management practice. Roughly 65% of all the manure is held in the lagoon, and altering the state of the current anaerobic lagoon to covered for the dairy lactating cows in Common Farm resulted in a significant reduction. The total reduction of 241 tons of methane per year, which is nearly a 25% reduction, which could be a really quick and cost-effective solution for Shelburne Farms. Looking forward, the results of this research has set the foundation for further advancements of this project at Shelburne Farms, and in the future, likely lab-scale testing and fieldwork will be done to generate biochar reduction potential values specific to Shelburne Farms before implementation of any alternative cost and energy and life cycle analysis would have to be done, but it's likely we will work alongside Marshall to develop the optimal waste management alternative for Shelburne Farms. Thank you for listening.